In this lab, we're going to be testing the enthalpy of combustion for solid magnesium. The problem, of course, is when you burn magnesium, magnesium burns with an incredibly bright flame, and most of the energy that's released is through ultraviolet radiation. Calorimetry cannot measure that energy. So instead, we'll be using additivity in the sense that we will be doing two separate reactions, one with magnesium and one with the product of its combustion, which is magnesium oxide, and we'll be mixing these into separate calorimeters with hydrochloric acid. Each of the reactions will be measured by a thermometer, and then we can take the enthalpy calculated values and solve the enthalpy of combustion using additivity. In order to do that, we're going to have to do two different reactions. The first reaction will be to take a piece of magnesium and weigh it on our scale. The specific mass of magnesium is not crucial because the molar enthalpy of reaction with hydrochloric acid will take into account the mass of magnesium used for the reaction. We can see there's slight fluctuations in the mass, possibly due to air currents in the room, but we will settle on a mass of 0.13 grams. At this point, we're going to take our calorimeter and we're going to put 50 milliliters of 1 mole per liter hydrochloric acid into the calorimeter. This hydrochloric acid will react with magnesium, and the resulting solution of magnesium chloride can be assumed to have the same specific heat capacity as water, as one of our calorimetry assumptions is that aqueous solutions can be calculated with the specific heat and density as water. So we'll place in our hydrochloric acid, 50 mils of hydrochloric acid. We're going to be using our vernier temperature probe here. So we'll place the temperature probe in the acid and we'll hit collect. Collect is going to give us the initial reading of the temperature of the hydrochloric acid, which we can see to be just above 22.5 degrees, about 23 degrees. Now with the thermometer in the solution, we will add our piece of magnesium and allow it to fully react with the lid on our styrofoam cup calorimeter. As it reacts, we will swirl gently in order to distribute the energy throughout the solution and to help the reaction of the hydrochloric acid. And we can see as it reacts, the temperature begins to climb. By observing through the lid, as well as listening for the bubbles, we can qualitatively say when the reaction is complete, and then take the highest reading on our temperature graph, which will indicate the full reaction and the greatest amount of enthalpy released from this reaction. So as the reaction begins to slow down, we can start to see the temperature decrease in slope a little bit and begin to slow down its growth rate. It is important to be patient to gather the highest possible temperature, as the temperature change is part of the error that can occur when calculating enthalpy. Using a digital thermometer such as this one, we have very accurate readings for temperature change. And we can see there that the temperature begins to plateau. Once it does plateau, and of course now in the colder room temperature it will begin to descend, That is going to be considered our maximum achieved temperature, just slightly under 35 degrees. So we can stop, and we can get our maximum temperature to be 34.8 degrees Celsius. We're then going to redo this experiment, but instead of using solid magnesium, we'll use magnesium oxide. So once again, we'll return to our scale, this time with a weigh boat, and we will tare the scale and add about 1 gram of magnesium oxide. Now, in order to weigh properly, we must take the weigh boat off the scale before adding the magnesium oxide so that the powder is not poured onto the scale. With a mass of 0.97, 0.98, we are close enough to the 1 gram. And again, the exact mass is not crucial, as the molar enthalpy of reaction with magnesium oxide will take into account the mass. So the mass of magnesium oxide that will be added will be 0.97. Once again, we'll use our styrofoam cup calorimeter. We will pour in another 50 milliliters of hydrochloric acid. Taking care to get the meniscus right at the 50 milliliter mark. And we will turn on our wireless device again. And record our starting temperature once again. Without the graph, we can see the starting temperature is 22.9 degrees Celsius. However, or 23 degrees Celsius. We'll wait a second, allow it to reach a thermal equilibrium. We will use the graph to indicate when the reaction is complete, so we know when to take the final value for the highest temperature achieved. So 23.0 degrees Celsius being our starting temperature. We will then take our 0.98 grams of magnesium oxide and dump it into our reaction flask here, and we'll start our graph. Again, we will swirl to help the reaction. And this time we can see that the rate of change of temperature is much greater, and this of course is due to the powder that was added. With its incredibly high surface area, it reacts at a much more rapid rate. Already we can see a little plateau. We'll make sure that the reaction is fully complete, swirling one more time. But we do seem to be decreasing, and so we'll stop and we'll collect the highest temperature, which is 38.0 degrees Celsius. With these data, you can now calculate the molar enthalpies of reaction for magnesium oxide and hydrochloric acid, as well as the molar enthalpy of reaction for magnesium and hydrochloric acid. You can then continue to solve for the molar enthalpy of combustion of magnesium using these data in an additivity equation.